Welcome to the part 2 of infrared spectroscopy. Here you have one reaction you already know. This condition gives you addition reaction to this double bond as a syn addition. And you know you're adding hydrogen and the OH on the same side, syn addition. But also, you know, this has a regioisomerism, and you get the anti-Markovnikov addition. So one of the isomers you get is this. And you get the hydrogen on the more substituted carbon, and you get the OH on the less substituted carbon. You get secondary alcohol as a product from alkene. And you want to run this reaction in the laboratory, and you need to find out whether your reaction is going smoothly or not. And if you are thinking using only TLC, it is limited, you know, to detect the alcohol on the TLC plate. So you may detect the disappearance of the reactant on the TLC, but you're not detecting appearance of the product. And if you even see something on the TLC other than the reactant spot, it's not necessarily is this compound, and you don't know. So that's why IR can be useful when you intend to monitor the reaction. And as we practiced all the time, the reactions taking place around the functional group. So your functional group in the reactant, the double bond is disappearing, and you get the alcohol instead. So those are the functional group you are focusing on if you are using IR, or if you want to know, you just confirm the product you get during the reaction is alcohol, and if that's enough for you, the IR is the instrument that you are choosing. But if you want to know more details about other parts of the molecule, then you know in the IR you need a polarity to detect easily with the IR. Another part of the molecule, they're not as polar, so getting information about other parts with the IR is not as easy, and thus IR is not as useful. That's when you need other instruments such as an NMR. Anyway, if you decide to use IR, then what's the technique it's taking for you to get good elucidation of the structure? Well, here I listed some. First, you have to analyze the functional group like we did, you know, double bond changing to the OH. First, you have to check if your functional group is a polar, then it's easier to detect. If it's not, then you have to be careful when you assign a certain signal as certain functional group that's not as a polar, because that's not as a trustable as a signal for polar functional group. And also you need to know types of bonds: single bond, double bond, triple bond, and whether you have light atoms or heavy atoms, because that's affecting the signal. So you need to find out what functional group that you are looking at. Then you need to remember that I'm going to show you, but what are the typical feature of the signal for each functional group. So once you know the typical ones, you can assign certain signals with the confidence and other things, non-polar ones, with a care. Also, some cases you have to expect potential variations on those peaks, even the trustable strong peaks. The signal can shift on the x-axis at that, potentially due to the resonance, or during the changes the isotope is replacing certain atoms and etc. Also, the intermolecular interaction is able to change shift or broadness or even intensity of signal. Also, the big molecules may have a secondary and tertiary structure, such as coils or beta sheets. Even in the smaller molecules, you could have a gauge interaction favored over anti-interactions, and so on. Also, you can have some potential variations when your molecule, the functional group, is embedded in the nonpolar environment or mixed with the polar environment. That can also cause some variations. So for the product, what signals you expect, you need to doing that by analyzing functional groups you have. So I obviously will look at the polar one first, because those are the trustable ones. So OH. What else you see? CO. And the rest of them are not as a polar. So you can see some CHs and some CCs, carbon-carbon bonds, right there. And the variety of CH on the sp3 carbons you see, and some of them are CH3 giving unique signal, and the CH2s also giving unique signals, but we're not getting into that detail for sophomore organic chemistry. So this much of analysis is good enough for product. Then soon we'll be learning the typical feature of each signals, so you can either construct the IR in your mind, predicting how the IR spectrum coming out of the machine should look like. Or when you got certain thing, when you interpret that, you need to use the typical feature with some expectation of potential variation. And if you practice one more time with the reactant, what do you see? I would say the most polar one or obvious one would be CH, but the carbon's not sp3, sp2, little more electronegative one. Or the sp3CH is also there, and you can notice CC double bond and carbon-carbon single bond. Yeah, those are the functional groups you want to notice, and then you will be able to tell, among other things here, what you need to check first if you learn the typical feature of the functional group on the spectrum of the IR. If you have molecule with the 2 atoms only, how many vibrations you can think of? It'll be just vibration, stretching vibration like this, right? There's only one. But if you happen to have, 3 atoms in the molecule, which is rare for organic compound. Organic compounds are much more complex than this, right? But if you do, how many actually can you think of? Different types of vibration. So actually the answer is there are 4 different modes of vibration. So I'm not gonna go through this our class is not going to be in this. If you are taking 300 level analytical chemistry course, you need to be able to analyze these things. But I'm just going to give out the answers for particular cases, then I'll move on. So this is the formula for linear molecule, like a CO2. In this exercise, you are basically considering the degree of freedom. Each freedom is corresponding one mode of vibration, and that's equals to the number of signal you expect on IR. And when you use the formula, this letter N represents how many atoms you have in the molecule. So you can see when you have 3 atoms, you plug in 3 times 3, 9, minus 5 equals 4. So you have 4 different modes. So let's figure out how they vibrate. But I want you to make sure that you know that when you have 2 different things, right, like NH2 for example, you don't have one vibration here, the other vibration there separately. It is the whole functional group. They move together a certain way, and that collaborative movement is making up one mode. So when you have these 2 side atoms moving this way together and this central atom moves also same direction, then what happens is the whole molecule is shifting this way. So it's not considered the vibration because you're not changing the angle or distance between the atom and the bonds. You're actually translating. You're moving around instead of vibrating. I hope you can tell the difference between translation and vibration there. So in collaboration, this guy in the center must move this way in order to not moving in the coordinate but changing the distance between this. They're getting closer while these 2 get apart. So it is actually vibrating that way. You can imagine, right? The 2 and guy in the middle like this. Oh, not that much, but like this, like this. Yeah, for this mode you have 1. Then I'm not gonna spend time too much. When these are moving away from the page, going into the page, this one can come up, okay? Or when this one moves this way, they can move that way. So they don't actually move in the coordinate as a molecule, but they change the distance and the angle. And when this central one's not moving, you can actually have these 2 moving out in this way. So those are the 4 modes you can have. So when you have partial charges on these atoms, if you actually mimic the motion and you are able to calculate the dipole moment changes because you are changing the distance, that way you can create like the idea which mode will have a stronger intensity. I hope you remember that, like a more polar functional group will have a better interaction with the light. But now you get deeper concept of the polarity. The polarity doesn't stay constant like electronegativity. As they vibrate, depends on their modes, the polarity change. So a certain vibration will give more polarity for same functional group, and some modes will have less polarity, so it will have a weaker signal. So 4 signal, and they're not identical frequency. Also, their intensity of the signal at a certain frequency, they're not also identical. And when you have a non-linear molecule, which is always 99% of the case for organic chemists, this can be water, but we never have a water spectrum. So it's better saying this would be CH2 and that central carbon's bound to other stuff, you know, in that kind of case. You see the CH2 functional group can have 9 different vibrational modes. You expect 9 signals for CH2. They are around same range of the frequency, but they're not identical. Also, their intensities are all different. And some are changing just the distance of the bond, but some are like scissoring, changing the angle. And like these, one going up and the other, but central ones are not moving, so it's like twisting, right? And these two are moving same direction, like wagging, right? And these two also like this rocking, right? So all kinds of vibrations possible, and you need to remember CH2 would not have 1, 2 vibration. You have to apply these formulas, and you can come up with different modes, and many vibration modes are expected, only even for 3 atom functional group, like a CO2. CO2 in the carboxylic acid as well. Alright, with this slide that we used in the previous video, I want you to remember in harmonic motion, like this oscillation in the IR that we try to detect, you need to have the physical model, the molecule, having certain frequency, and we want to detect it, then our light should have also the same frequency. So light frequency and the object motion frequency, and we need to use this formula to get the information out of the IR spectrum. So on the spectrum, you're going to be reading similar to this frequency on the x-axis, and reading that number, you can connect it to the force constant and the reduced mass of the functional group. So I'm gonna have to start using this formula. So here I wrote CH2 with the 2 connections with the other part of the molecule, and since it's non-linear, you expect 9 different frequencies in 9 different modes of vibrations. So which means though you will have a 9 different value of the nu here, but reduce the mass is the same because whatever the mode you are encountering, you have the same atoms. Meaning only difference you have is the K value, force constant. The force constant is how much force you need in order to change them, right? So in each mode, you are changing their motion of the same mass. So which one is more difficult to do it or easier to do it, that determines the frequency. So different x value on the IR spectrum will eventually telling you this. For same functional group, since the same functional group had the same reduced mass. So in the application, for example, if you are doing docking experiment of a drug or a substrate with a certain enzyme, when the molecule is free in the solution like water or blood, the CH2 is rocking freely, for example, one mode, right? And then when it's docked in a certain active site, then the space is confined with a certain charge around of the protein, then the motion is limited as the motion get hydrogens of CH2 closer to the wall of the active site. Then the potential energy is making the vibration more difficult, meaning the K value will change. Then the frequency of the vibration will slightly different. Therefore, if you keep track of this signal, if you could, then you can tell whether the CH2, including drug, is free or bound. Also, by measuring the intensity and apply the Beer's law, you can also calculate the concentration that's free and the concentration of the molecule that is bound. So you can calculate the equilibrium of the two states as well. And in general, the force constant for stretching vibration, that's changing the bond distance, is greater than the K value for the bending. So bending is a lot easier than changing the bond length. That's probably because the bending is not changing the distance between atoms. So attraction of the electron is about same for the bonding phenomenon. But stretching case, you have to partially break the bond to get stretched. So it takes more energy to overcome those electrostatic force between nuclei and the electron, which means with a greater K value for the stretching, you expect the frequency to be a little higher. So how high it is? For CHs, the stretching signal normally comes around 3000 reciprocal centimeter, plus minus some number, depends on the situation. We'll talk about it soon. And for bending vibration, they're normally coming below even half of this value, 1450 to 1500, right? So even below this, that's where you expect all kinds of bending vibrations. That much is weaker. And for CHs, your stretching is around 3000. So stretching. Then among the stretching, for example, the asymmetric vibration, when you have two hydrogen bound to the central carbon here, for example, when you do stretching, that's a symmetrical or asymmetrical. The asymmetrical vibration usually have a greater K value, meaning a greater frequency compared to the symmetric ones. So asymmetric ones and the symmetric ones. Okay. And I want to draw your attention on the Morse curve, showing the potential energy of the bond. Okay, with the two atoms, the distance between them here will change their potential energy, obviously. There is a maximum optimal distance for the most stable and lowest potential. That's right there. So at this bond distance, that's a regular bond length, you get the lowest potential. So they like to be here. But because the atoms and molecules have a kinetic energy, they're not static, they're always moving around. So it depends on how much they move around and changing the distance. You can imagine one of the lowest vibration, you can imagine, say, was this much, right? It's going from this smaller or that larger. So this is optimal distance, for example, most stable, but they're not static ever. So they have a little vibration. So stretched, compressed. When the normal bond distance measure was about here, right? The vibration is there, so they have this much of a displacement. So you are imagining they move around a little bit, and that's the movement they have. Then the molecule is actually experiencing this much of a potential when they are compressed or stretched. But when they come back to the stable regular bond distance, then they go down in energy. So they go up and down as they stretch. You know, this way energy is going up, down, even up, down, up, and so on. That's what you see here. So they draw a line in quantum level. This is the minimum vibration you need to have. They say vibration ground state. Then if you give photon that matches with this frequency, then you can make it go to the higher frequency, meaning you now have a more vigorous vibration with the more variations in the bond. So you experience more potential energy up to here. If you keep giving more energy, that allows them to have a quantum jump, right? Some moment you have too much stretching going on, so it's gonna break apart. So the distance increase infinitely, but the potential energy stays the same because they're not bound anymore. So they are free from each other. Bond is broken. That's when you have heat given up, or a photon given, not heat given up, I'm sorry, heat put into the molecule. As that's when we do, say, E2, right? You give it energy. Or when you do radical initiation, you apply heat or photon. So when you do that, they dissociate. That's what's happening, and the Morse curve is showing that. The reason for me to introduce this here before we actually look at the spectrum is because you sometimes see V0 go to the V1. That's what we see on the chart. You know, that's what I'm gonna teach you as the norm, you know, the general typical feature. So that's the delta E that we are talking about right here. But time to time you see this jump, because these days the spectrum is ran with the laser, or even some other cases the frequency happened to be, you know, twice of the other functional group. Then this could happen for the functional group that you're not trying to aiming at the moment, but it just happened. So this transition had twice of more energy. It's supposed to be used for other stronger vibration, but this weaker vibration happened to absorb it, but it went up twice. So this one right here is called overtone. You actually see the signal that's twice of this frequency on the IR. So you need to know that when you read the spectrum, there is some signal that does not quite match with something that you are presuming the structure to be. Then you have to consider the option you may have overtone. Here I'm trying to show you the IR spectrum starting from 4000, I think I mentioned once in the intro, to 400 for typical organic compound. You can go beyond, depends. And I hope you remember in the previous slide, the frequency is proportional to the force constant of the bond and then the reduced mass. And I want you to remember the typical one using this equation so you can remember more effectively, and especially when the time comes to think about the variations, you can do that, you know, finding variations and thinking of some ideas of fitting the structure into the data. You become much more effective in doing that. Also, don't forget the y-axis is the absorbance. That's the measurement consists of the three factors we talked about: the number of the functional group you have, not the concentration, right? You have a sample, then the sample concentration is the same, but within the sample you could have a many same functional group. Then the functional group concentration is higher than multiples of the concentration of the compound, and the sample cell size will be same, but the absorptivity will be different for all functional group. The polar one's gonna give you more stronger intensity of signal, and the weaker polar functional group gives a smaller size. So you need to keep track of the size and also location. And then there is the factor of fatness, how fat it is, how sharp it is. And that is due to the intermolecular interactions or the environments that the molecule is in, or solvent and things like that. Here, so I split the spectrum into 4 sections, and let me make a point here. The bond strength of the single bond is roughly about 5 times 10 to the 15 dyne per centimeter. That's how much force you need to change about a centimeter of the bond length. So when single bond has about 5, double bond has about twice of value, and the triple bond has about 3 times. So simply speaking, you can say single, double, triple as 1000 and below, and 2000 and below to 1000 as a double bond, 3000 to 2000 as a triple bond. So 1000 single, 2000 double, 3000 for triple. So if you see signal around here, around there, you know what type of bond you have according to the, K value. However, you should not think it strictly that way, because a carbon single bond is not as strong as a carbon-oxygen single bond. So there will be some variations, depends on their atoms. And that's true for double bond also, and the triple bond as well. And the factors for frequency that determining the energy gap from the ground state vibration to the first excited state vibration in the Morse curve, there is reduced mass, right? So if you think of these regular organic compound, you have a carbon, nitrogen, and oxygen, those things, their atomic weight is like 12 for carbon, and the 14, 15 for nitrogen, and then 16 for oxygen, and so on. So the effect of the carbon becoming nitrogen, becoming oxygen in SN2 or something, it doesn't affect in the frequency that much, though that may change the polarity and changing the intensity. So you can say, oh, I got the substitution because the intensity of the signal changed, though the signal appears at around same area. However, what if you have a hydrogen instead of carbon? You have a carbon and the hydrogen compared to the carbon and carbon. The difference in the mass unit, if you think about it, right? 12 versus 1. So reduce the mass, simply speaking, if you compare root 12 versus root 1, the ratio is how much? The ratio is about 3.46-ish. So more than 3 times, almost 3.5-ish. So if you replace the carbon, one of the carbons with the hydrogen, then the frequency due to the reduced mass, it changes more than 3 times. So when this becomes smaller with the hydrogen 12 times, then the value of the root will be about 3.5 times bigger. So single bonded carbon hydrogen will appear here. So you can see all the carbon hydrogen signal comes here, not due to the K value. There is a little change, but it's mostly by the reduced mass. Then you are saying, how about chlorine and bromine if you have on the carbon? Okay, you try that, and the ratio is not that great. And the CCl and the CBr single bond will be still in this box. But it's more to the smaller number, around 600-ish. So you expect the CBr, CCl around here. But what else is changing? Carbons are neutral almost, but they are polar. So the intensity of the signal increase by much, while the CC single bond is small peak with the bigger frequency value. So this is how you understand the general placement of the signals for a certain functional group based on the K and the reduced mass that constitute a certain functional group. So instead of memorizing the numbers for each functional group that's given in some textbooks or online tables, I want you to remember this chart with the concept I'm trying to give you here. So let's go to the highest frequency functional groups. If you have a hydrogen, whether you have a carbon, oxygen, nitrogen, the difference is small because the reduced mass of the if you take a root of it, for carbon and nitrogen, oxygen, they're not that different. And they're all coming in this first box. But what different is OH, it could come in here with a very strong and the sharp. If they're not hydrogen bonded, okay, free OHs. Say you have a protein with the OH functional group residue embedded in the lipophilic bilipid layer of the cell, then you have no water or something, then it can be sharp. But if you have hydrogen bond happening, then the hydrogen bond is creating weaker or stronger OH bond. So you experience variety of hydrogen bonding, making variety of the strength of the OH. So you have all kinds of frequency is absorbing the light, interacting with the OH bond in different strength of the K value. So you will get the broad and yet as a strong absorption for OH. So this is a H bonded alcoholic OH functional group signal. But time to time you see the OH is making stronger hydrogen bond, then it could have even more broader. But most of the time OH of alcohol is confined below 3000, and the location of the tip will be around 3400, 500 in the middle of this block. You don't need to know exact number. It actually depends on a lot of factors. So memorizing the number is useless. Have a visual memorization here. So certain cases like a carboxylic acid, they are more efficient in making hydrogen bond. If you draw out the structure, you can see they can actually go far deeper passing 3000 and go to the even 2000 sometimes. It can be even more shifted. Depends on the strength of the hydrogen bond that is also affected by the environment. Okay, so this can be OH, most likely in carboxylic acid when they are making H bond. So I should say H bonded OH in carboxylic acid. Then what other atoms found with the hydrogen in organic compound? You can see some of the polar ones other than OH will be probably amine, right? The NH. And NH could be the one in the secondary amine, real NH. That shows about like 50% or even less, but it depends on the polarity. So the polarity of the NH again can be altered by environment or the neighboring functional groups, and what conformations you have with the other groups, that changes the molecular dipoles and stuff, right? So I cannot say for sure, but it will be around this and this location in the middle ish, but more to the 3000 ish, but not really close. But if you have an NH2, you expect that to be like double the mountains for NH, the NH2, the primary amine. So you have two signals. When you read the frequency, you can say from something 3000 whatever to 3000 whatever, or you can read the maximum value. You draw a line here, you see 3100, something like that. But there is no rigid number, so I don't like you to remember those numbers again. I want to make sure that you know it has two signals for NH2, not because it has two bonds, right? There are two or more vibrational modes, like SCH2 we talked about, and some of them are showing intense signals and some of them are not. So one of them turned out to be asymmetric stretching vibration of NH2, the other one as a symmetric vibration. So asymmetric stretching vibration will be like this, two hydrogens going like this while they're attached to the nitrogen, and symmetric ones are like going like this, right? So those are the two modes made by the three atoms. Then we have CHs. I said the CHs are around 3000. They're not far deep in the 3000, 4000 block, or deep in the 3000 to 2000 block. They're around 3000. And they're not intense. And also, I like to remind you that there are three types of CHs. When the CH is on the sp3 carbon, sp carbon, or when hydrogen is on the sp2 carbon, or when it's on the sp3 carbons. So the sp carbon is most electronegative, so the bond is most polar. Therefore, the A value will be greater because more polar dipole moment is greater, meaning the epsilon value is greater. So that expected to give you greatest signal. How about the location, you may say? Well, the sp carbon makes a stronger bond with hydrogen compared to others, so the K value for the sp carbon and the hydrogen single bond is greater. So, they are coming around here. I don't want to give you exact number again. It's closer to 3100, or even it could be 3200. But if you have a resonance and others, variations happening, then it could be somewhat lower. But anyway, and you normally have one hydrogen on the triple bond, unless you are looking at ethylene group molecule. So anyway, you have only one. But CH2, sorry, the sp2 could have a CH2 on it, or even one more hydrogen on the other end of the carbon of the double bonds. You could have a 3 even. So you expect more than one of the sp2 carbon having hydrogen. So when this is a triple bonded hydrogen, I don't want to say this is always weaker, so it should be smaller than that. That's useless, because unless you have a sp carbon and sp2 carbon together, ordering them is not useful at all. So even when you have them together, I don't want to order them by sp2, because again, it depends on the neighboring group of particular bond, the triple bond or the double bond. So I would rather go by the intensity and overall situation that we will develop the concept again later. So you expect 1 or 2 or maybe even 3 for it depends, but for sp2ch stretchings, these are stretchings. And for CH3H's, it's weaker bond, so it's always almost 99% of time smaller than 3000. They're almost 99% of time greater than 3000, but close to the 3000. So you expect a little one for sp3 hydrogen. However, you never see this unless you have a special molecule. You normally see huge molecules showing this type of a spiky signals. Why is that? When you look at even octane, right? How many sp3 CH bonds you have? A lot of them. So many CH bonds you have. So again, you have the same concentration of the molecule, but within the molecule, this particular functional group, you find them multiple times. So the concentration of specific functional group is making the intensity of the particular signal greater. So you can consider that the concentration of the particular functional group is equals to concentration of the molecule multiplied by number of the functional group within molecule. Then you expect this to be much greater than usual intensity considered size. And then all these little spikes indicates one modes of a stretching coming from the CH2s. So there are a lot of different CH2s included in this peak. All right, what are the typical triple bond that comes in this box? You don't see many triple bond in organic chemistry. You have a carbon-carbon triple bond, carbon-nitrogen triple bond in the cyanide, right? Nitrile group. That's it. And both of them shows a signal, not even 2500, more to this side, like this. It's not as intense as you would think. So carbon-carbon triple bond is usually smaller than carbon-nitrogen because of the polarity. So carbon-nitrogen can be, taller. Let me change the color. That's for the carbon-carbon triple bond. That's for the carbon-nitrogen triple bond. But it never is as big as OH. And for carbon-carbon triple bond, if molecule is a symmetric like this, carbon-carbon triple bond with the same structure on both sides, then the dipole moment cancel, so the molecule becomes nonpolar, molecular dipole moment becomes smaller, then the peak becomes smaller. If you put the triple bond at the terminal, then it's not symmetrical, so triple bond tend to give a somewhat more intense signal. This way you get more detailed information about the structure, whether the triple bond should be in the center or the terminal. Coming to this block for the double bond, you have to be careful because I mentioned earlier, around in the middle, 1450. That's when you start to have bending vibrations. So everything below here, you have to read in the risk of mixing up with the bending vibration signals. So those stretching signals can be buried or competing with the bending vibration signal. So when you give some assignment, you have to be extremely careful. That's not trusted area. So what are the double bonds you see in organic chemistry? Well, you see a lot of carbonyl group, right? Ketone, aldehyde, ester, carboxylic acid, amide, all kinds. So, you know, carbonyl groups are polar, so it's going to be one of the strongest, intense, but they're not as broad as the hydrogen ones, because they're not making hydrogen bond as much. So it's not as sharp as these guys who never makes any intermolecular interactions, but not as much of hydrogens. So CO double bond. This comes around 17 something. Plus minus, it could be 100 or 200 even. Okay. So it's safe. Even when this shift by some reason, it could be near 1500. And then, you know, it's usually higher than bending vibration region. That's a nickname for that is a fingerprint region. Fingerprint region. Because you can match this to find out rather than functional group, but other feature has to do with the structure, because bending has to do with the structure rather than functional group. Anyway, so the CO double bond, even with the other circumstances, is usually above the 1450, so you can see, but even it went under it doesn't matter, because your bending vibrations are not giving strong signals. They're usually weak or medium size of signals. So CO double bond is safe. You're not getting confused. So you can always check carbonyl with a IR. Another double bond that you have to worry about is a carbon-carbon double bond. They are not as polar, so it's small. And it happened to be, if you calculate the K value and reduce the mass in this formula, the number is around 1500 plus minus. So this can be usually around 1600 and below. It could go as low as 1400. So right at this bending vibration region, and the intensity is also not trustworthy. So I'm not gonna trust this. Then when do you use this? And this is the point where it becomes complicated for reading spectrum. If you suspect the presence of the CC double bond, what do you have to check? If you have the sp2 carbon, then you may, not always, but you may have a hydrogen on it, which appears here, right? sp2 carbon hydrogen. So if you see any peak here, and you have something you are suspicious about, then you can say, yeah, I have this. If you have a chance to run NMR, then you want to double check with NMR, because NMR is showing this more clearly. That's when you learn other techniques and you already see how the reading spectrum is going to be, right? You cannot rely on one. In order to have some confidence in your interpretation, you gotta connect with the other spectrum. But anyway, here you might say as a beginner, well, how do you know this is a sp2CH or sp3CH then? Well, if this was a PCH you worry about. Or what did I do here? Excuse me. This should be triple bonded carbon with a hydrogen. Excuse me for that. So then, if this was true, then you expect this signal here, because you have sp carbon. So without this peak, you saw something here and you see something there, then connecting them, you can say I have double bond, not triple bond. If you see something there and you have one signal here, then it cannot be double bonded carbon hydrogen. So you see how the logical thinking start to kick in. Okay, for the last box, for the single bonds, we don't trust this area, and only few single bonds are strong enough to show over the bending vibrations. So the bending vibrations I can mimic like this, sharp, something like this. In order to be recognized as a trustable, valuable signal, it should be taller than this, deeper than this, right? So one of the polar functional group that gives the high epsilon value would be, let me use red, this tall and rather little fat signal of CO single bond. Depends on the resonance and other elements. Well, say you have a resonance here, right? Due to the double bond you have, for example, you can have a more than single bond. That means K value increase. That means the frequency increase. That means the energy of the gap for excitation increase. So you expect this one shift this way. So how far this can go? It can go as far as even 1300. So I would remember as a CO single bond around 1000 maximum value for single bond, plus minus couple hundred easily. Okay, more to the plus side most of the time. Then you have a chlorine giving somewhat broad signal but intense, and the bromine a little lower, and they are normally around 700 something to 600 something. That's enough. I like to add two little things here before I flip to the new page, and I think I should do it in next video. But when you look at these OHs, that's broad, time to time they are coming in with the other signals, because you have a carbon hydrogen always, like this. So what happens is this: you're supposed to have symmetric peak ideally, but you see some shoulders here. So then you can imagine, oh, ideally this broadness giving symmetric broadness here, so this much of the signal is additional. So what's coming here in this number? So you are finding just OH if you don't know that. But if you are aware of this fact, little spiky or shoulderness, OH plus other thing here, and they could be either CH on the sp carbon or sp2 carbon. For the broader carboxylic acid one, you expect a lot more spikiness, even this like, and then like this. Then also there are additional peaks. And there's also other CHs coming around here. That's aldehyde CH. That normally gives two signal. Symmetric, asymmetric stretching of the oxygen, hydrogen on the carbon. So one comes at 28 something, almost 3000. The other one comes at 27 something. And the way I show will tell you, If you don't have any sp3ch, you don't have this big sp3 signals, you can see both. But most of the time, this signal here for sp3ch bonding stretching, it comes passing 2800 easily. So normally this is buried. But if you see something little outside or at the skirt of this peak, then you have to sort of guess and hypothesize, I might have aldehyde. Okay, you don't want to ignore those little peaks. Then how do you confirm? Well, I said in the same light, you need to check whether you have a carbonyl group. So you go where? You go 1700 area. Then you can find it, CO, then you know you have aldehyde. If you don't see it, then that's not the aldehyde. You can check the presence of the carbonyl or aldehyde with the HNMR or the carbon 13 NMR or the UV spec. You can confirm it. The last one, the double bond of carbon shows a signal around here. I said it's not trustable, but you can do it in conjunction with this signal here. But sometimes you see more than couple, a lot of, several spikes here. And then you also see medium to little taller peaks, more than one, and more to the 1600 side, like here, couple of them. Then it's over bending vibration and you want to trust it, but it's too close, but there are multiple of them. Then you check it here. Oh, I have several of them. Then you actually have aromatic ring with the many hydrogen. It's not because you have many CHs, each gives one signal, right? As a group, these hydrogens have many different vibrational modes. Yeah, so that's the signal you find here. Even for many CC double bond peaks here, that's also a collaborative bending or stretching vibration that gives signals here. All right, I ended up making longer than I thought, but I had to do it because I didn't want to split it. But next and the last, probably for IR spectroscopy, I'll deal with some advanced feature, like when you have some variations. Let me search. Yeah, like I showed on this slide, we did this, right? You know how to analyze the functional group, and you know the typical feature, the location on the X, and then the intensity on the Y, and whether they're narrow or broad. But now we need to pay attention to some potential variations like these. Then I'll move on to some examples. So I'll see you next time.